Okay, here we go. 11.2, one-sided limits and continuity. Two different topics in one lesson. All right, so this looks familiar. We've done limit problems numerically by doing a table, and so we're going to revisit this in order to link to something new. So coming from the left side, as I get closer and closer to 0, let's think. I've got a -1 here, so maybe a negative, how about a negative 0.1? As I'm getting closer and closer to 0, negative 0.01, negative 0.001. And if I put that into my calculator, I'm going to get on the top 0.2, and on the bottom divided by negative 0.1, which is just going to give me a -2, right? If I do the same thing here, I'm going to continue to get a -2, a -2. So we would say that from the left, the limit is approaching -2. And so, new concept. If you notice, it's the same limit problem, but something new is we see this minus sign right here. And that tells us we're doing a one-sided limit, and the minus tells us we're coming from the left side. So we're taking the limit of this function coming from the left side. We already know how to do it. We've done it a million times. Maybe not a million. But from the left side, it's equal to -2. So what do you think we're going to do on this side? We're going to do coming from the right. So if we have 0 and there's a 1 and we're coming in from the right, we'd probably start with 0.1 because that's pretty close, and then 0.01 and then 0.001, right? If we plugged a 0.1 in, we'd get 0.2 on the top divided by 0.1 on the bottom, which would give us a +2, right? So this side, as we're coming in, we're going to be a +2. So now we can write, when they ask us, hey, what's the limit of this function as x is approaching 0 from the right, because that plus means a one-sided limit coming from the right, we'd say that's equal to 2. Now, is there a limit? Is there an answer for this official limit problem? If we've got coming from the left, the limit is equal to -2, and coming from the right as we're approaching 0, the limit is equal to +2. Do we have a limit for the whole function? No, we don't. It does not exist. But we do have a one-sided limit coming from the left and one-sided limit coming from the right. And so I pulled up some of the numerical tables that we did before. And same thing here. We've got the original limit not existing, but when we did it from the left, right, it kept going and going. Oh, what's it approaching from the left? It's approaching -infinity. Sometimes on a test or in your homework, it'll want to know why something does not exist, and you would put, because it shoots off to -infinity. Same thing coming from the right. It's just getting larger and larger. It's shooting off to +infinity. But our answer, our limit, really is that it doesn't exist. So this is a case where the original limit didn't exist. And even as we're approaching, as x is approaching 4 from the left, the limit of the function doesn't exist. And even as we're approaching the function, as x is approaching 4 from the right, the limit of the function does not exist. So it's interesting because as we're talking about one-sided limits, sometimes, let's get rid of this and this, the one-sided limits exist, but the actual limit doesn't exist. And in this case, not only does the actual limit doesn't exist, but both sides, both the left limit as we're coming from the left and the limit as we're coming from the right does not exist as well. And let's look at another case. This is from our first lesson when we did limits graphically and analytically. I'm sorry, graphically and numerically. So we discovered that the limit of this function as x approaches 2 actually existed. It was -4. Not only that, coming from the right, the limit was -4, and the one-sided limit coming from the left was also -4. So this is what is really interesting, that in this case, the one-sided limit, the limit coming from the left, is the same as the limit coming from the right, which is the same as the limit that's coming from both sides. That doesn't have a one-sided limit restriction. So what did we discover? We actually discovered that if your one-sided limit coming from the right is equal to the one-sided limit coming from the left, then the limit of the function actually exists. So let's go back real quickly and note that the limit from the left is equal to the limit from the right, which meant that the whole function actually had a limit as x is approaching 2. And in our other two examples, the limit did not exist coming from the left, coming from the right. So the function did not have a limit as x approaches 4. And then with this one, whoops, the left-sided limit was not equal to the right-sided limit, which meant that the actual limit of the function as x approaches 0 did not exist. So fascinating, right? Those are one-sided limits. So what does that mean? This baby's so cute. I'm not sure what discussion we're supposed to be having right now, but I think right now we're going to go ahead and look at a piecewise function. So this is the first time we're looking at a limit of a piecewise function. And you'll notice that I put in from the left and from the right. So this is just kind of, if we took these things away, we would just have a piecewise. But I thought I would connect with what we just learned, which is this. When we see x is less than or equal to -3, well, we know we're approaching, oops, got rid of the -3, but we're approaching -3. And so when x is less than or equal to -3, that means we're looking at the limit from the left, right? And when x is greater than or equal to -3, that means we're looking at the limit from the right. Either way, we're going to need to graph it because it asks us to. And I'm not going to get really technical like I did in class because there's really no need to be technical about this graph. It is just a sketch. That's why we're going to be able to get the information we need just from the sketch. So I see that it's a quadratic. I see the -3. The first thing I'm going to do from the left is I'm going to make a table, and I'm going to start with -3. If I go ahead and plug -3 in, this is where I'm going to need a calculator. Let's see, I'll have -9. Let me find a calculator. I don't want to rely on just my brain when it's in front of everybody. So let's see, -9, and then we'll have a +30, and then we'll have a -24. So we end up with -3. Okay. So we're going to have -3, -3. There's my first point. Let's go ahead and pick a -4. We'll do a few points. In class, I made everybody actually graph it using, we factored it, we found the zeros. I think we can just get away with doing the tables for now. So let's see if we plug in a -4, it's going to give me a -16, and then plus a 40, and then minus a 24. And that gives me a 0. So there's one of my zeros. That makes sense. 2, 3, 4. And let's do -5 and call it a sketch. So we're going to plug in -5. So that's -25 plus 50 and minus 24. So that leaves me with 1. So I'll have -5, 1. And I have a feeling that I'm going to come down at -6. Yes, I am, because if I actually, there is something for finding the zeros, because right, our two zeros would be, yep, our two zeros would be a -4 and a -6. Let's see, actually, let's plug in a -6. We're going to get a -36 plus a 60. And minus a 24. Yep, that's our other 0. Okay, so here we go. We're going to, that was probably we did it faster in class, didn't we, when we were factoring. You can do it either way. You can find the zeros, you can make your table. Either way, we're done. We know that coming from the left, this is what's happening. It's coming this way. It's heading towards, it is heading towards -3. So we know that's true. So now let's look at from the left. So we're going to plug in, oh, and notice that we put a solid circle because this is a solid line right there. All right, coming from the right, we're going to go ahead and plug in -3, and we get that that's also a -3, which is good. That's what we're looking for. Some people wanted to put an open circle here, and you could. I mean, it's really already filled in, but if you wanted to do it as a placeholder, we could do the rest of the line as a slope. We could go, what, up 2 over 1 and draw a line from there, or we could continue to plot another point. Either way, we can see that coming from the left and coming from the right, both of the limits are equal to -3. So we're kind of running out of room with what we would write, but the limit of this function as x approaches -3 is equal to -3. So once again, the limit exists because the left-sided limit is equal to the right-sided limit. Okay, so same thing here. I know that this part is from the left because it says x is less than or equal to -1. So it is linear. That's going to make it easier. We'll start out with a table. We'll plug in -1. So we'll get, oops, let me put my tick marks on here. Once again, it's just a sketch to help us to see what the limit is. Okay, so from the left, we plug in the -1, and we're going to get what? 1 minus 3 is -2. So we'll have -1, -2. We are going to put a solid dot in there. And then we know that it's the slope is negative, so we're going to go up 1 over 1 this way because I'm only interested in what's going on to the left of -1. And so then let's look at from the right. So we'll switch this up. Even though it says x is greater than -1, our table is going to start with -1. We put -1 in, we're getting a 0. All right, that's bad news. We do have to put an open circle here. We didn't before because they actually lined up and there was already a filled in dot there, but this time, yep, we need that open circle. The slope is 1, so we'll go up 1 over 1. All right, so coming from the left, we are approaching -2. Coming from the right, we are approaching 0. But that's okay because I just noticed something. It's only asking us from, whoops, I just erased it. It's only asking us from the left. So the limit of this function, where we're approaching -1 from the left, that is equal to, as we're coming from the left, equal to -2. If it asks us for the limit of the whole function, we'd say it does not exist. All right, yay, we're done with one-sided limits. But next is continuity. So let me check on the time real quick. All right, we're doing great. So here's a formal definition of continuity. There are 3 things that have to exist, and you do need to know this. Usually I put f of c as defined, but we're okay with this definition. F of c exists. So there has to be an actual value. Now c stands for any x, any particular x that we're looking at. So if we're looking at f of 2, there has to be a value for the function when x is equal to 2. That's the first thing. The second thing is that there has to be a limit that exists for that function as x is approaching that c, that certain number. And then the third thing is they have to both be equal. So I'm going to go to the next slide to show you some pictures that will help you with this concept, but this is a formal definition of continuity. It says continuous at c, so we're looking at continuity at a certain point, which sounds kind of crazy, but if you think about a function, it's continuous at every single point, well then it's everywhere continuous. So let's talk about that. None of these 3 pictures are continuous. Let's just set the record straight. What does a continuous function look like? Well, if that's my graph, then a continuous function could be like a quadratic or a sine graph or a linear graph. A continuous graph, we know it intuitively when we see it. It doesn't have holes, it doesn't have asymptotes, it doesn't have gaps, like all these guys. These are not continuous. So let's see why these are not continuous. When we look at number 1, we see, first of all, that there's no value at C. So this is a graph, right? Here's the number C, and we see that, oh, there's no value there. So f of C does not exist, and that is the reason why this one is not continuous. Is there a limit? Absolutely. Okay, this one's a crazy mess. F of C does not exist, and the limit of the function as x approaches C does not exist. So that is not continuous. Here, this is really nice. F of C does have a value. See that little dot? That's the value of the function when x is equal to C. So it does exist, check. And there is a limit of this function as x approaches C that actually exists. It's kind of hard to tell, but it looks like it's 1, 2, 3, 4, 5. So check, are they the same? No, f of C does not equal the limit of, I'm running out of room, but you know what I mean, of f of x as x approaches C. So these are 3 examples of functions that are not continuous. All right, so this is a step function, and it's got its continuous places, but is it continuous at 1? No. When x equals 1, it is not continuous. No. X equals 2, it is not continuous. There's a lot of points of discontinuity in that one. Okay, let's see, did I skip? All right, and look at this, at x equals 2. It's not continuous. There is a value for x, but there's no limit. That function is not continuous. Same thing here. That looks just like what we did. There is a value when x is equal to 2, right? F of 2 does exist. It equals 5. And the limit of this function as x approaches 2 is equal to 3. So that's great, right? But 5 does not equal 3. So it is not continuous. All right, hopefully you got, oh, there's another one. There's a limit, there's no value. That means there is no continuity at x equals 0. Oh, a beautiful continuous function. It's continuous everywhere. All right, so determine if each function is continuous by using the 3 conditions. There is a graph here. I'm not sure, they're not asking us to graph it, so we can use one of 2 methods. The first thing is I'm going to look to see if there's actually a value at -2. So I'm going to go ahead and make my table. I'm going to plug in my -2. When I plug that in, I get what? A 4 minus an 8 is -4 plus 5 is 1. That sounds good. And then I'll go ahead actually and do a little bit of a graph just to get a visual. Okay, so at -2, I'm at 1. I'm going to fill in the circle because of this equal sign down here. I'm looking at it from the left, so I'll real quickly do a -3 just to see what direction it's taking. And I'm going to definitely have to pick up my calculator. So I'm going to have, let's see, I'll have a 9 and then minus a 12 plus 5. And we have a 2. So the -3 will have a 2. And I'm just going to imagine, because it's positive, that it is going up that way. Now I'm going to look at the second part. I am still, once again, even though there's not an equal sign, I start with -2, just like I did before when we were doing the earlier graphs. And when I plug -2 and I get -4 plus 5 is 1, that's awesome, right? I could put an open circle here just to remind myself, but look, it's filled in, so there's going to be continuity there. Then I'm going to use my my slope information, so I'll go up 2 over 1. If you didn't like that, then you are free to plug in some more points. Do we have continuity here? Absolutely. We have that the limit as we're approaching from the left and from the right, the limit of the function as we're approaching -2 is equal to 1, both from the left and from the right. We know that the value of the function when x is equal to -2 is also equal to 1. And we know 1 equals 1. So yes, they are continuous. Now, if a function is not continuous, there are two different types of discontinuities, because we call them either they're continuous or they're discontinuous. So there's two different types of discontinuities. There are removables and there are non-removables. And I'm going to suggest that you pause this, that you write it down, and that you can see from looking at the pictures what we're talking about. And then we're going to, after you pause, come on back and we're going to do some examples with this. Okay, welcome back. So for example 5, we're going to think about chapter 2. And with chapter 2, it didn't ask us about discontinuities and removable and non-removable. It just asked us to graph them. So that's what we're going to do. We're going to look at this function. The first thing we would do if it was chapter 2 is we would say, find our vertical asymptotes. We would take the denominator. We would set it equal to 0. We would, right, because that's where our vertical asymptotes are going to be located. We would factor, we'll have a +4 and -3, and we would think that we have two vertical asymptotes at -4 and 3. But then I can hear it through the screen. Ms. Overby, simplify. All right, let's simplify. If we simplified this function, look what happens. What happened in chapter 2 if one of our vertical asymptotes got simplified? We simply said this guy is not a vertical asymptote, it's a hole. He's a vertical asymptote. This one's a hole. So we could stop and we could go ahead and graph this, and you can if you want to, but we already can stop and say, wait a minute, we know that there's going to be two discontinuities, right? There's a removable discontinuity at x equals 3, right? Because that's the hole. So the hole leads to a removable discontinuity. And then we know that we have a non-removable discontinuity at x equals -4, because we learned from the last slide that vertical asymptotes, not only does a vertical asymptote pretty much stop the continuity, but it's a non-removable one. All right, that's it. And you have a practice sheet to go with it for homework. Thank you for joining me. I will see you in class.